Welcome to section 16.4. So just to remind you guys, I'm going to be skipping around in the section itself, and so make sure that you guys are watching all the videos. So that way you know which subtopics you guys are responsible for. So we're going to continue our discussion on solids. Now what I want to talk to you guys about are something called lattices. Lattices describe the arrangement of atoms inside a solid structure. For example, what you can envision is that your atoms are arranged in a cube, where each individual atom occupies a corner of a cube. We can also have it in different shapes. For example, we can have it occupy a hexagon and then another hexagon on the bottom. The lattice is going to tell you the long-range arrangement of our atoms in our solid material. So we can describe the lattice using simple diagrams like this, or we can expand and make it grow bigger and bigger. Now, what you guys can do is you guys can go ahead and describe the lattice using a cell that you repeat. So this is called the repeating cell. So let's go ahead and look at a two-dimensional lattice. So the lattice that I want to describe is one where I have a green, red, and so I'm alternating the spots between a green sphere and a red sphere. Or you guys can envision this as a big sphere and a small sphere. Now, just like in describing our polymer, what I can do is I can take a small subset of this lattice and say that I'm going to repeat that subset over and over. And this is called the repeating cell. So what you guys can see is I can duplicate what's inside this box over and over, and I will generate the rest of my lattice. Now, there's a special type of repeating cell, and that is called the unit cell. The unit cell is the smallest repeating cell that reproduces the whole lattice. Now, understand this unit cell might not be obvious to you guys. For example, I would not consider this a unit cell, because what I can do is I can draw an even smaller cell that would reproduce the whole lattice. And so what you have to be careful about is it might not be something pretty, it could be something off angle, and it could be shapes that you wouldn't consider perfect. So let's start off with our first quiz, and tell me if the black box that I've drawn on here represents a repeating cell. So, gentle people, what you'll see is that A and B actually do represent a repeating cell. And I can draw that cell over and over, and it repeats the rest of that lattice. But let's take a look at option C, which was not considered a repeating cell. Okay, ladies and gentlemen, the first thing I'm going to do is draw my repeating cell. So I'm going to start with the cell, and I'm going to draw the contents of that cell. So here's the cell that you see in choice C. Now what I'm going to do is I'm going to go ahead and duplicate that cell. So what I have is a red in the top corner and the red on the bottom corner. I have a blue on this bottom corner and a blue in this top corner. And what you guys will see is we start to see the problem here. If I keep repeating this, what I will get are half atoms, where it's half blue and half red. And so this does not happen in the lattice that you guys saw. And so the problem is, if I put these unit cells together, it does not repeat the rest of the lattice. So that's why C wasn't a repeating cell. Okay, ladies and gentlemen, let's go ahead and talk about packing. When we start packing atoms into a solid structure, what I want you to envision is that each one of those atoms are a hard sphere. So a way to think of this is pretend that you have a whole bunch of baseballs or tennis balls or basketballs, and you are trying to organize them inside of a box. So let's think about the first example. I want to do something called a closest packs structure. A closest packed structure means I want to pack the most amount of material into a given space. So if I start out with one basketball, what I can do is think about how many basketballs can I surround this one basketball with. Now, if you have some coins like a penny or a quarter, you can play this game. You can go ahead and ask yourselves, how many pennies can I surround one single penny with? Now, what you guys will find is regardless of what coin you use, penny, quarter, nickel, you'll find that you can put 6 things around a circle. And the same thing is going to happen with a sphere. If I get a basketball, the most basketballs that I can do in one layer is going to be 6 basketballs surrounding that one basketball. So this is going to make my first layer. Now the next layer is going to be the same thing. I'm going to use this same configuration, 1 in the center and 6 things around it. When I go ahead and put that second layer on top of my first layer, I'm not going to put it right on top of each other. Now you can play this game. If you take 3 basketballs, what you will notice is that there is a little divot or hole. What you can do is you can nestle another basketball in that little space. And that's what's going to happen with the second layer. You're going to nestle that second layer in between the gaps that the first layer has made. So you can see it like this. To do this, I have to offset the second layer by a little bit. And so what I get is layer B. So my first layer, we'll call layer A. My second layer, layer B, a little bit offset. Now what I'm going to do is I'm going to put a third layer on top. Now I have a couple of choices, but in this particular packing, I'm going to go ahead and layer the third layer directly over the first layer. And I'm going to do the same with my fourth layer. The fourth layer is going to be directly above my second layer. And so my layers are going to be A, offset B, A, then back to B again. This type of packing is called hexagonal closest packing, or HCP for short. This is one of the ways where we can pack spheres as close as possible. Now, if I look at this structure, this involves a lot of atoms. What you guys will see is that I have about 7 atoms, 4 layers. That's 28 atoms describing this structure. Let's see if we can get a unit cell out of this. So what your book does is it goes ahead and packs the structure and it pulls out a unit cell. Now this right here is called the primitive hexagonal unit cell. This right here will duplicate the rest of our structure. So sometimes it's really hard to see 2D representations of 3D objects. So right here, I'm going to use a program that shows you guys the 3-dimensional layout of that HCP unit cell. What you guys will notice is the face is a rhombus, the back end of it is also a rhombus, and in the middle of these 2 rhombuses is another atom. So what I can do to describe this is I can use what's called fractal coordinates. So let's go ahead and learn how to use this. So right here is what we call a fractal coordinate. It is going to describe the placement of the atoms in that unit cell. So the first thing you guys will see is that it shows you a rhombus. On one of the corners, it says 0, 1. This is telling you the location of each one of the atoms in the unit cells. So what the 0 says is that there is an atom closest to you. That means it's 0 unit cells away. So I can put 1 atom here, 1 atom here, 1 atom here, and 1 atom here. And so those are represented by these 4 circles on that fractal coordinate. Now what you guys will notice is it says comma 1. And so what that says is duplicate this same structure 1 unit cell away or at the end of the unit cell. So if I were to draw the unit cell out, 1, 2, 3, and 4, those are the 4 atoms in the back. Now what you guys will notice is there's 1 atom that is given the designation 1/2. That means that there is an atom halfway in the unit cell. It's not on one of the corners of the rhombus. So what they're talking about with that half designation is this guy right here in the middle of my unit cell. What you will notice is he is halfway in to my unit cell. So just to help you with the fractional coordinates, here are my zeros. These four right here are closest to you. And then here is the comma 1 in the back. They are 1 unit cell away from you guys. All right, ladies and gentlemen, let's talk about the other closest packed structure. In this slide, we're going to be talking about the cubic closest packing structure, or CCP. Now, to do this structure, we're going to do the same initial steps. So again, envision your basketballs or your baseballs, your hard spheres. I'm going to make one layer first. That one layer has one central atom, and I'm going to put 6 atoms surrounding it. For the second layer, I'm going to do the same thing. I have one atom in the center, 6 around it, and I am going to offset it. So A, then B. Now my third layer, instead of putting it right above A, I'm going to put it offset from both A and B. So this is going to generate a new staggering. It is not over A, it is not over B, so I'm going to call this layer C. Now the next layer, the fourth layer, has to go right over A, and then the fifth layer has to go right over B. So what I get is ABC, ABC with my layers. With every different layer, I am offsetting it differently. And so what we can do again is we can go ahead and see if we can pull out a unit cell out of this. So the unit cell that gets pulled out of CCP is called the face-centered cubic. And this is called the FCC unit cell. So this is one of the strange ones where the packing doesn't match the name of the unit cell. So let's go ahead and take a look at this. So right here is the fractal coordinates. Why don't you have this slide up, and I'm going to show you things on the 3D model and you can watch along. All right, ladies and gentlemen, here is the FCC unit cell. So I hope that you guys have the fractal coordinates, and so we can go ahead and follow along. So in this case, what we have is a perfect cube. So I'm going to look at the front of this cube along with the fractal coordinates. What you will see on the fractal coordinates is I have a 0, 1. And that is going to be on each one of the corners of my square. So 1, 2, 3, and 4. And so you see a set that is 0 away from you. And also you see one that is 1 unit cell away from you. 1, 2, 3, and 4. So that's why they labeled this one 0, 1. Now, the next thing you'll note is that there is also another one that corresponds to 0, 1, and that is this guy right here in the center of my face. And this is why it's called face-centered cubic, is because on the face of each one of these cubes, you guys will notice that there's an atom. There's one atom closest to you, so 0, and then there is an atom 1 unit cell away, so that's the comma 1. Now, if I were to look on the face of my face-centered cubic, you'll notice that I did not describe this atom right here. This atom is halfway into my unit cell on the top. So if you guys look on the fractal coordinates that I gave you on the slide, you'll see that it describes this atom right here. There's a dotted circle and it says 1/2 because it's halfway into my unit cell on the edge or on the side of my square. And so here you guys can see the FCC unit cell. Now, one thing I want to note is that there is nothing in the center of the cube. It is completely empty. All right, gentle people, the next thing I want to talk about is counting atoms inside a unit cell. And so this is a very popular MCAT question and standardized test question. If I draw an atom fully within the unit cell, this counts as one atom. Now, if I have a unit cell and an atom is on the face of my unit cell, what this counts for is half an atom. For me to generate that whole atom, I would have to draw the next unit cell over. And so half of the atom is in one unit cell, and then the other half of the atom is in the other unit cell. If an atom is on the edge, it counts for a fourth of an atom. And again, what you can see is that if I draw the unit cells all around here, you can see that I fully generate that thing on the edge, and I will need 4 unit cells to complete that atom, which means that a fourth of an atom is in each cell. And then lastly, if you have an atom on the corner, it counts for 1/8. And so if you look at my picture right here, try to envision that whole atom. What you will notice is only 1/8 of it is generated in this unit cell. For me to fully generate that atom, I will have to draw 8 unit cells. Now, all those unit cells are going to have to be surrounding this one right here, and then I will finally generate that whole atom. All right, ladies and gentlemen, let's do some quiz questions. So here's the first thing I want you guys to tackle. So let's say I have calcium, and calcium has a unit cell of face-centered cubic. So here's the fractal coordinate, here is a 3D model, here's a space-filling diagram. So 3 ways for you to see that same unit cell. Tell me how many calcium atoms are in this unit cell. All right, ladies and gentlemen, let's take a look at this picture because I think this is the easiest one to see. What you will note is I colored the atoms slightly differently based on their position. Now, each one of these spheres are a calcium atom. What you guys will notice is that I have 8 corners, and the corners are represented with red spheres. So, I have 8 corners, and each one of those count for 1/8. So if I were to go ahead and do the multiplication, that turns out to be 1 whole atom. Now what you guys will see are the atoms on the faces, and they are represented by these gray spheres right here. Now if I count the number of gray spheres, there's 6 of them, and remember, an atom on the face counts as 1/2. And so if I go ahead and do the math, that means that there are 3 calcium atoms. 1 plus 4, that means that there are 4 atoms or 4 calcium atoms in this unit cell. All right, gentle people, let's do something a little bit more involved. So what I want you to do is tell me the density of this unit cell. So we're still going to have calcium, and I'm going to give you a little bit of information. Calcium weighs 40 atomic mass units. You can get this off the periodic table, and this corresponds to 1.67 times 10 to the negative 24th grams. The radius of calcium is 197 picometers, and 1 picometer equals 10 to the negative 12th meters. So these right triangles that I've shown you guys are going to give you a little bit of information on how to solve this problem. So remember what density is. Density is going to be mass over volume. And make sure you get the units correct. All right, gentle people, so let's go ahead and tackle this problem out. So like I told you guys, density is mass over volume. So let's go ahead and try to figure this out. So the mass is going to be the calcium atoms in my unit cell. So based off our last quiz question, what we know is that there are 4 atoms of calcium in my unit cell. Now, each one of these calcium atoms weighs 40 AMU, and what I gave you was a conversion, and that was that 1.67 times 10 to the negative 24th equals 1 AMU, And so what I can do is I can get the mass inside my unit cell of those 4 atoms. And that happens to be 2.672 times 10 to the negative 22 grams. All right, gentle people, the next thing we need to do is we need to figure out what the volume of my unit cell is going to be. So let's take a look at that picture that I gave you. Now what you guys will see is that I have a cube. And so if I want the volume of the cube, that means that I want to take one of the edges and I want to raise it to the 3rd power. The length times the width times the height. Or in other words, I want to take one of these edges of the cube and I want to cube it or raise it to the 3rd power. Now, what I didn't give you was how long that edge was. What I gave you was the radius of each one of these calcium atoms. I can see how the edge relates to the radius of these atoms. So if I look at the face of a face-centered cubic, this will help me figure this out. So what we can do is we can start at this corner atom. This corner atom is going to have a distance of r. And then I have the central atom on that face, and that has a distance of 2r, and then finally the last r right here. And so that is going to make a diagonal line across one of the faces of my cube. And so the length of that is 4r, and I can use a right triangle. So the edge right here is going to be my edge, so that's going to be D in this case, and then it also has another edge of D. So both my edges are equivalent because I have a cube. So let's go ahead and do a little bit of math. So looking at that right triangle, what we can do is we can go back to good old Pythag and his theorem. So what it says is that if I take the side of a right triangle and square it, add the other side of a right triangle and square it, that is going to equal the hypotenuse squared. And so now what I can do is I can do a little bit of math. So this turns out to be 2d squared. This is 16r squared. I can take the square root and divide by 2, and what I end up with is that the edge is going to equal root 8 times r. Now remember what I said, that the volume of a cube is going to equal one of the edges cubed. So that means that the volume is going to equal root 8 times r raised to the 3rd power. So all I need to do is put in my radius. When we look at density, we want it in cubic centimeters. So 197 picometers equals 197 times 10 to the negative 12th meters, which is equivalent to 197 times 10 to the negative 10th centimeters. So that means my volume is going to equal root 8 times 197 times 10 to the negative 10th raised to the 3rd power. And that means my volume is 1.73 times 10 to the negative 22nd centimeters cubed. So now, ladies and gentlemen, I can finally do my mass over volume. So there was the mass that I calculated. I'm going to divide it by the volume, and I end up with a density of 1.54 grams per cubic centimeter. This should have been choice B for y'all. All right, ladies and gentlemen, let's continue our discussion with some other types of unit cells. The next unit cell or packing that I want to talk about is something called the body-centered cubic packing. So here is the unit cell for the body-centered cubic. There are atoms on each corner of a cube. And then there is one atom here in the center of the whole structure. Now, this is not a closest packed structure. There is a bunch of empty space in this, But what you guys can do is you can calculate and verify that there are only 2 atoms per cell. So for you guys that want the 3D model, here you guys go. Here are all the 8 corners, which you guys see there's an atom, and in the center of my unit cell is 1 atom there. Make sure you guys look at that fractal coordinate diagram and see if you can make sense of that diagram with this picture right here, or this 3D model that you see. The last unit cell that I want you guys to know is called the simple cubic. Again, this is not a closest packed structure. There is a lot of empty space in this one. With this one, what you guys will see is I have a cube, and then on every single corner of the cube, I have an atom. Now, there is no atom in the center of this one, and so if you guys go ahead and try to count this, go ahead and try to count how many atoms are in this unit cell, and what you guys should get is that there is only 1 atom in this unit cell. And so here you guys go. Here's the 3D model. Make sure that you guys go ahead and take a look at that fractal coordinate diagram and see if you can make sense of it. All right, gentle people, what I'd like to do is end with a summary of all that we've talked about. So what I want you guys to be responsible for is I want you guys to know these 4 unit cells. I want you guys to know how many atoms are in each one of these cells, and I want you to note that 2 of the ones that I talked about are closest packed structures. That is the unit cells that are face-centered and the primitive hexagonal. The atoms make up 74% of the space in there, and there's only about 26% of empty space. The 2 other unit cells, the body-centered and the simple cubic, you'll note they are a lot more emptier than the closest packed structure. The last thing I want you guys to know is the nearest neighbor in each one of these cells. So you guys can memorize this, or you guys can look at the unit cells themselves and figure it out. For example, let's take a look at the body-centered cubic. So if you look at this central atom right here, the one that I'm coloring in, what you will note is that there are 4 atoms on top, and then there are 4 atoms on the bottom. So the number of nearest neighbors that it has is really simple for this one. It has 8 atoms surrounding it. Now, that doesn't go for just this central one. Each one of the atoms in the body-centered cubic are going to have 8 nearest neighbors. Now, you won't see it in just one unit cell. You guys are going to have to draw the other unit cells around it to see those neighbors. So right here, 8 nearest neighbors. Well, I hope that made sense to you, Chem 1C. And again, remember to stay safe.